Welcome! In this quick explainer, we're going to unlock one of the biggest secrets in chemistry, how energy is the driving force behind pretty much every chemical reaction. We're going to look at reactions that heat things up, ones that cool things down, and that little hidden barrier every single reaction has to overcome just to get started.
Okay, so first things first, we've got to get our terms straight. In chemistry, when a reaction is happening, we call the actual chemicals doing the reacting the system. Simple enough, right? And everything else, I mean everything, the beaker, the air, the thermometer, even you watching, that's all the surroundings. You have to get this distinction down, because it's the key to everything else we're about to cover.
And here is the single most important rule in the entire universe that runs this whole show, the law of conservation of energy. It basically says that any energy that our system loses has to be gained by the surroundings. And you guessed it, if the system gains energy, it must have swiped it from the surroundings. It's a perfect, closed loop, no exceptions.
So this back and forth transfer of energy between the system and its surroundings really only happens in one of two ways. And that gives us two totally different types of chemical reactions.
See, that energy has to go somewhere. It can either flow out of our reaction, which we call an exothermic process, or it can be pulled in, which we call an endothermic one. Let's dig into what that actually means for the world around the reaction. Okay, so an exothermic reaction is one that gives off energy. The easy way to remember this is exo sounds like exit. The system is pushing thermal energy out to the surroundings. And that's exactly why the temperature around the reaction goes up. It gets hotter. Because the system is losing energy, we say its change in enthalpy, or delta H, is negative. And you feel these kinds of reactions all the time. That amazing warmth coming off a bonfire, that's combustion, a classic exothermic reaction. The heat from a chemical hand warmer, that's usually a neutralization reaction. Even your own body, right now, is basically a little furnace of exothermic reactions through respiration. They're all just releasing energy into their surroundings.
Now for the total opposite. An endothermic reaction takes in energy. Think endo, like enter. It literally pulls thermal energy from the surroundings and sucks it into the system. And what happens when you take heat away from something? It feels cold. Since the system is gaining energy this time, its change in enthalpy, delta H, is positive.
So what about the reactions that make the world feel a bit chilly? Well, photosynthesis is the big one. It's pulling in the sun's energy to create life itself. And think about this. Anytime you melt an ice cube, you're watching an endothermic process. That ice has to absorb heat from your hand or the air, just to change from a solid to a liquid.
So how in the world do chemists actually picture this energy journey? Well, we use a really simple but super powerful tool called a reaction profile diagram. You can think of it as a map of the energy levels from the very start of the reaction to the very end.
Let's look at the map for an exothermic reaction. See how the reactants start off with a lot of energy, up high? Then, because the reaction releases all that energy, the products end up way down at a much lower level. That big drop you see? That's all the net energy that gets given off as heat. And no surprise, the endothermic profile is just the mirror image. Here, the reactants start out low on our energy map, and because they absorb energy from everything around them, the products finish up at a higher energy level. That upward climb represents the positive delta H. Now, you might have noticed something on both of those maps, a kind of hump they both had to get over. You see, a reaction doesn't just happen. It needs a little push to get it started, and that push is called the activation energy.
So why doesn't a piece of paper just burst into flames on your desk? It's because of this really fascinating energy barrier. Think of it like an entry fee to start the reaction. Its official name is activation energy. It is the absolute minimum amount of energy that particles need to have when they collide to actually react. Without it, they just bounce off each other, and nothing happens.
For an exothermic reaction, I like to think of it like pushing a giant boulder over a small hill just so it can roll down a massive mountain on the other side. That little push you need to get it to the top of the first hill, that is the activation energy. Yeah, it takes a bit of effort, but it unlocks a way bigger release of energy on the way down.
And here's how we show that push on our map. The activation energy is always measured from where the reactants start all the way up to the very peak of that energy hump. This is why you need a match to light a fire. The wood has tons of energy to give off, but first you have to provide that little push, that activation energy,
to get the whole thing started.
Okay, so we've covered the key players, the different paths, and the maps they follow. Let's pull this all together into one super clear summary.
This table right here is your ultimate cheat sheet. For exothermic, energy gets transferred out, the surroundings get hotter, the sign of delta H is negative, and the products end up with less energy. For endothermic, energy gets transferred in, the surroundings get colder, delta H is positive, and the products end up with more energy. It really is a perfect side-by-side comparison.
So, we've seen that activation energy is basically the key that unlocks all the energy stored in chemicals. But you know, this idea of a small push unleashing a huge change, it isn't just for chemistry. I mean, think about a single domino starting a massive chain reaction, or one small idea that sparks a revolution. Where else in the world do you see it? A tiny input that overcomes some barrier to create a massive release of energy. It's definitely something to think about.